Hi everyone, welcome to this video on formula writing. We've seen some examples of formulas already, but what we're going to do is learn how to systematically write them down in this video. The first thing we generally do when we're writing formulas is try and work out if the substance we're dealing with is ionic or covalent. It's the easiest way to make things transparent for us. Sometimes the lines are a bit blurry, but in this topic, most of what we will do will either be definitely ionic or definitely covalent. When we're doing this, one of the easiest ways to do this is look for a metal. If you can see a metal in its structure somewhere, it's probably ionic, if this is a compound, that is. Another exception to that is you may also see the ammonium ion, which is NH4+. If you see any of these then in a compound, then chances are the compound is ionic. If it's primarily nonmetals, then it's probably covalent. But there are some exceptions, of course, but this is what we're going to use for the moment. So the first ones we're going to look at are the ionic compounds. So for example, we've got 4 questions over here. How do we write the formula of sodium chloride, magnesium fluoride, calcium oxide, and aluminium sulfide? Now in the question, if I hadn't already told you these were ionic, you'd have to look through and work out if they're ionic or not. These are clearly ionic because they all have a metal in them. Sodium, magnesium, calcium, and aluminium are all metals. The next thing we want to do is work out what the valency of each of these ions is. And to do this, we look at our valency table. We can also use our periodic table for monoatomic ions like this, but easiest thing to do, look at the valency table. Sodium, for example, is in the +1 column, so it has a valency of +1. Chloride has a valency of -1, and that then gives us a starting point. The next thing we need to do is work out how we put these positive and negative ions together so that the overall charge is balanced. The positives and the negatives have to cancel each other out. We can do this intuitively, or we can use something called the swap and drop method. If you're doing it intuitively, for example, here, sodium chloride, we've got +1 and -1. They kind of cancel each other out, so their formula is quite simply NaCl. The swap and drop method is something slightly different. What you do is you look at the number in front of that charge. If there's no number, it's a 1. You take those numbers, you swap them over, and then you drop them down to the other side. So for example, you take that 1, you swap, and you drop, you swap, and you drop. So that should give you Na1 and Cl1, or NaCl. Ones don't get written. Okay, next example, magnesium fluoride. Look them up in your valency table. Magnesium is 2+, fluoride is 1-. The swap and drop is particularly useful here. So what do? You take the 2, swap it over, take the 1, swap it over, and that gives you a formula of MgF2. The answers are in red. So when you put your answers down at the very end, they should have no charges on them. They should be completely balanced, as you can see over here. Next up, we have calcium oxide. Calcium is in the 2+ column, so it's got a valency of 2+. Oxide is 2-. Again, swap and drop. So we take the 2, we swap it over, take the 2, swap it over. Now, when we do this, we'll get a formula of Ca2F2. But in a case like this, we also have to go a step further. Ca2O2. In a case like this, we also have to go a step further. If they can be reduced any further, if they have a common denominator, they should be. So what we need to do is reduce this, divide them both by 2, and turn this into CaO. It's the only catch with this swap and drop method, that you have to reduce it if it can be reduced. But again, if you do it intuitively, you'll notice that calcium's 2+, oxygen's 2-. If you have one of each, they balance each other's charge out. And finally, we leave the best for last. Aluminium sulfide. Sulfide means it's sulfur. So what we've got here is aluminium is 3+, sulfide is 2-. We've got to swap them over. Do that, and that should give you Al2S3. And that's your final answer for that one. Now, if you want to check, you can always make sure your charges stack up. So, for example, aluminium sulfide, if you have two aluminiums and three sulfides, as so, all up, you've got 6 lots of positives, so 6 plus, 3 plus, and 3 plus, and 6 lots of negatives, 2 minus, 2 minus, 2 minus. So overall, their charges are balanced the way you've written them. That's a handy way to check if you want to make sure, but as long as you've done one of these methods, it's fine. The key thing is to generate a formula. Slight complication when it comes to ionic compounds is sometimes you might encounter a polyatomic ion in your travels. Polyatomic ion is basically a collection of atoms. They're bonded covalently themselves, but all together with their powers combined, they are an ion. An example of this is things like sulfate, SO4 2-. The sulfur and the 4 oxygens are combined together using covalent bonds, but together they've got 2 extra electrons, so that gives them a charge of 2-. They're an ion. And then you have things like carbonate, CO3 2-. You can also have a range of other polyatomic ions. The negatively charged polyatomic ions, they often end with the word ate or ite. So whenever you see ATE or ITE, an easy way to remember this is they ate some oxygens. There are also some slightly weirder named ones. So for example, hydroxide is an OH- ion, and then ammonium is actually one of the few positively charged polyatomic ions. It's NH4+. So here are some examples of ionic compounds with polyatomic ions in them. Have a go at doing these on your own if you can. Pause the video. Basic steps the same, swap and drop. There's an added level of complication though. So I've gone ahead and written down the valencies for you. You're welcome. What we're going to do now is swap those numbers over, just like before. So potassium has a 1 in front of it. Take it, swap it over. Sulfate has a 2, swap it over. That should give you a formula of K2SO4, just like that. Then when you go to calcium nitrate, you take the 2 in front of calcium and the 1 in front of nitrate, and you swap them over. Slightly added level of complication here. If you write it out as it is, you'll get Ca, one of them, and NO3. You need 2 lots of it, so you need to put a 2. The problem is it kind of looks like 32. So how do you get around this? You put a bracket around the NO3, and that then shows you've got 2 lots of the whole thing. Same deal for the next one, NH4 and O2. Take that 1, swap it over, take that 2, swap it over. That gives you a formula of NH4. You need 2 lots of it, so you put a bracket and then a 2, and then next to it your O. The next layer of complication comes about when we have transition metals. Transition metals, you may remember, have variable valencies. They can have multiple charges. So we need to have a way of getting around that. Examples of these are chromium, iron, and lead, as you can see here. The way we indicate these in the name is we put their charge in Roman numerals next to the name of the ion itself. So chromium 3, for example, means it's got a valency of 3+. Iron 2 is 2+. Lead 4 is 4+. This only is for metals, and it's only for positive ions. So generally, if you see a number, you can assume it's that number positively charged. When you write their formula, you go about it the same way as you do for the others. Pause the video and have a go. So here you've got chromium 3+ and F- from our valency tables, or just from reading our name. What do? Same as always, swap, drop, giving us, in this case, CrF3. You do the same for the other ions. So we've got iron and sulfate here. We take the 2's, swap them over. We take the 2, swap it over. Remember, it'll if we have the same number, or if we can reduce it further, we do. So instead of writing Fe2SO4 2, we write it as FeSO4. And then when we get to lead 4 oxide, it's Pb4+ and O2-. If we swap those over, we'll actually get Pb2O4, but we can divide that whole thing by 2 and end up with the formula of PbO2. So we've spent a lot of time talking about ionic compounds. Covalent compounds are just as important, but their formula writing is a lot easier. There's a few added complications, but for the most part, in the case of covalent, you just read their name and write down what they are. In the case of covalent, the name kind of tells you how many of that particular element are in there. So for example, carbon dioxide is covalent. We know it's covalent because there's no metals, all non-metals, and the word di means 2. So carbon dioxide means you've got 1 carbon and 2 oxygens. So CO2. Remember the number, how many of that particular element you have, go in the bottom right corner. Next up we have phosphorus trichloride. Phosphorus is P, chloride is chlorine, Cl, and then tri means 3 of them, so you put it down the bottom. Next up you have dinitrogen tetroxide. Nitrogen is N, and it's di, so there's 2 of them. Tetroxide is O, oxygen, oxide, and tetra means 4, so you put a 4 next to it. Dinitrogen tetroxide. Notice something else as well. What's common between the covalent compounds and some of the ionic is that the second element, in this case, ends with the word "ide." Right? So in covalent compounds, the second element ends with the word "ide." In ionic compounds, you do see ides quite often when it's the element by itself, when it's not a polyatomic ion. The prefixes for all these names are given below. So mono is 1, di is 2, tri is 3. You'll notice that everything beyond tri ends with an A. Tetra, penta, hexa, hepta, octa, nona, and deca. We don't need to know anything beyond that for this course. Sometimes we ditch the A when there's 2 vowels together in the name. Sometimes the A gets lost, but there's no real convention to that. An added complication with covalent compounds is a lot of covalent compounds, particularly the larger ones or the more common ones, they have something called a common name. It's not a systematic name, it's something that's just given a generic name. The best examples of this that we come across are water, ammonia, and methane. Water's systematic name would be dihydrogen oxide, but we don't call it that, of course. If you have time, I might actually share with you some of my lame dihydrogen oxide jokes, but not today. Ammonia is nitrogen trihydride, but we just call it ammonia. Methane is carbon tetrahydride, but we just call it methane. So these are some of the common names. You'll see more and more of common names if you go on and do organic chemistry, but for the moment, these are the only common names we need to know. And finally, the last layer of complication with covalent is what happens when you have something called a diatomic molecule. Fluorine, oxygen, nitrogen, and hydrogen, in their elemental form at room temperature, they don't actually exist on their own. They get lonely. They actually pair up with other fluorine, oxygen, nitrogen, and hydrogen molecules. As a result, they exist as something called a diatomic molecule, which means fluorine, elemental fluorine, is actually written as F2, oxygen is written as O2, nitrogen is written as N2, hydrogen is written as H2. Thanks for listening, everyone. Do as much practice as you can and ask your teacher if you need some help.